Hi, this is Mr. Asher, and this is for Chem 121. And this is the second video I'm going to make for Module 3 because we missed class on Monday due to the holiday. And I hope you had a good 3-day weekend. So today I'm going to go over covalent bonding. And last module we went over ionic bonding. And ionic bonding is when atoms lose electrons to become cations, positively charged, and other atoms gain electrons to become negatively charged anions. And then those anions and cations attract each other and stick together. And the thing to remember about ionic compounds is they may have a simple formula like table salt is sodium chloride, NaCl. So a positively charged sodium atom combined with a negatively charged chloride ion. And there isn't such a thing as a sodium chloride molecule. That ionic compounds exist in a big lattice, in a crystal lattice of, of, of many of these charged particles sticking together. Because you can imagine if you have a positively charged ball here, which is the sodium, and the negatively charged ball, which is chloride, coming together to join like that, you've got all of this negative charge out here for the chloride and all the positive charge out here with the sodium that could attract other positive and negative charges. So you get this lattice where you have positive, negative, positive, negative, positive, negative. And that's a big lattice. And in general, I'm going to share my screen now. That when you look at ionic compounds, you want to remember that they mostly form between metals over here. Remember, metals are down here over to the left, and then nonmetals up here over to the right. So for example, sodium and then chloride, table salt, is a metal, sodium, bonding with chlorine, right? And the reason these things ionize is because they want to lose one electron. Sodium wants to lose an electron so that its electronic structure looks like neon. Things want to become more noble gas-like. Chlorine wants to gain an electron to become argon. Oxygen wants to gain 2 electrons to look, at least in terms of its electronic structure, to look like neon, right? So those are ions. And most ionic compounds, there's some exceptions when we talk about molecular ions, but most ionic compounds are a metal from over here bonding with a nonmetal. And what happens is the nonmetal over here will take electrons off of the metal so that the metal becomes a cation, and this gaining electrons becomes an anion. That's the thing from over here. Right? Well, covalent bonding is different. And covalent bonding involves 2 atoms that are both nonmetals. And instead of one atom ripping an electron off the other, they share. So what can happen is that by sharing electrons, each atom kind of gets fooled into thinking it's got a noble gas electron structure, right? And I'll show you some examples of that. But it's important to remember that we're talking over here for covalent compounds is all we're talking about is really pretty much these compounds here, right? The nonmetals, carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, chlorine, selenium, bromine, iodine, astatine. And then some of these compounds here, boron, silicon, arsenic, tellurium, will form covalent compounds, boron and silicon in particular, right? So keep that in mind. Ionic compounds, the distinction is electrons are transferred from one atom to the other. In covalent compounds, there's no transfer of electrons, that the atoms share electrons. And I'll show you what that sort of looks like in phenomenology when I turn on my whiteboard. So that's what we're talking about in terms of covalent compounds. And remember, it's just these nonmetals. So what I'm going to do now is I'm going to turn on my whiteboard so I can make some drawings. And it's all the way over here. Right. New share, whiteboard. Okay, so remember we're talking about 2 nonmetals, and let's take a look at a very simple compound, chlorine, right? So chlorine, if you look at its electronic structure, it has 7 valence electrons. And remember, the valence electrons are the electrons in the outermost shell. Remember, in an atom, you've got the nucleus, and then electrons exist in these shells around the atom, right? So in the first shell, there's 2 electrons, and that would be helium, or hydrogen and helium. In the next shell, there are 8 electrons, and so on and so forth. And on the third shell, there's also 8 electrons, and then on the fourth shell, there are 18. And the farther out you go, the more electrons the shells hold. But anyway, and so atoms want to have a completely filled outer shell. They want to lose electrons, they want to gain electrons until they get to this filled outer shell. So chlorine has 7 electrons. It sits here. In the third shell, it's got 7 electrons and 8 fills the shell. And there's something we talk about called the electron dot structure. And with that, we write electrons in pairs around the atom until we come up with all the valence electrons, right? So chlorine has 7. Boron, which sits in the 13th period, has 3 valence electrons. Boron would have 3 electrons. So we fill them up, right? Carbon has 4. Nitrogen has 5. So and then you add 1 more. So that has a pair. Oxygen, for example, has got 6. So that is 1, 2, 3, 4, and then 5, 6. Doesn't really matter where you put the doubles at this point, but you do have to have 6. And carbon, if there's space available, the electron goes on an unfilled side rather than being paired. So carbon has 4 electrons like that, okay? Well, you can see that chlorine, which looks like this, right? It needs 1 more electron. A chloride ion in this thing would chloride minus, and it would have 8 electrons around it because it took an electron from somewhere else, right? 8, right? But if now look what happens if we pair 2 chlorine atoms. 1, 2, 3, 4, 5, 6, 7, and then 1, chlorine, not carbon, chlorine. 2, 3, 4, 5, 6, 7. And you can see here, if the 2 chlorine atoms share those 2 electrons, then each one thinks it has a full valence shell. So it would be chlorine with the 2 electrons between them. Right? And when electrons are shared like this between 2 atoms, we call that a covalent bond. It means that the electrons are sharing the atom. Phenomenologically, you could think of this as in an atom, this isn't a great model, but if we have the nucleus here in the atom and the electrons in the shells are whirling around the atom, right? Right. So here's chlorine with all the inner electrons. We have 2 in the inner and then 8 around it here. And then we have 7 here. What happens in a covalent bond is you have the 2 nuclei and you still have the inner electrons going around each nucleus, right? And then on these outer electrons, there would be 6 in here on this ring. And then some of the rings, let me change color. Hopefully you can see this. Let's make it blue. Then now all of a sudden, some of these rings do this. So that instead of the electrons in this blue ring orbiting around one atom, what they do is they move in between the other atom. They move between each atom so that each atom sort of shares them. And there'll be 2 electrons in here because there's 2 electrons in between the atoms. And the only thing, the main difference between this and a typical sort of figure 8 orbit is the electrons spend more time in this region, which wouldn't be true in a true classical orbit, but they spend more time here than they do out here, right? So when the electrons are in here, each nucleus feels that electron in there and it pulls itself towards those electrons. And that forms the bond, the electrostatic attraction between the electrons, which are now spending time between the two nuclei, and then the and the positively charged nuclei. And the reason these inner electrons don't take part in that is because they're more tightly bonded and they're closer into the nucleus, right? And the electrostatic force drops off very quickly with distance. So that's what's going on with the covalent bond, is we're sharing electrons. And metals in general don't form covalent bonds because they want to lose their electrons so easily. It's just easier to just pull them off. So that's what happens, is you just get pulled off by the other compound and they form ions. And the other compound gains the electron. But here, for these two compounds, covalent compounds, they share electrons. So for example, oxygen, go back to black. Oxygen, remember, oxygen in its elemental form is O2. And so if you think about oxygen, each oxygen atom has 6 electrons. And what happens with oxygen is 2 electrons from each atom get shared. So there's 4 total electrons being shared by the 2 atoms. And now if you look, if we count the electrons to each oxygen atom, there's 2, 4, 6, 8. And over here, there's 2, 4, 6, 8, right? They're not really 8 electrons on each atom, but each atom thinks that there sort of are because of these 4 that are in between the 2, and these what are called bonding positions, bonding orbitals, right? So, and you could start to think about covalent bonding in all of this. So for example, methane is CH4, right? And what methane looks like is carbon is here with its 4 electrons around it, right? And then what happens is each hydrogen comes in with a single electron. Right? And hydrogen wants to have 2 electrons because it's in the first row. So this to hydrogen sort of looks like it's helium to hydrogen. And now carbon has got 8 electrons around it, or at least it thinks it sort of does, right? And so in all of covalent bonding, what's happening is atoms are trying to get themselves to a full octet by sharing electrons. And you can do all sorts of compounds. For example, phosphine, pH3, and phosphorus, remember, has 5 electrons. So it's got 1, and then 1, 2, 3, right? And then hydrogen comes in, each hydrogen having 1 electron, and fills up its shell. Ammonium is the same, has the same outer electron structure as phosphorus, NH3. So we have N, and then H, right? So that's what's going on with covalent bonding. We're sharing, and the number of molecules that are available as covalent compounds is really limited to just a few atoms from the upper right part of the periodic table. But because carbon is such an integral part, and because these covalent compounds can form longer chains with each other, there is a huge chemistry associated with them. All of biology is involved mostly with covalent compounds. So going back to the periodic table for just a moment, the important thing to remember is that these molecules here are going to follow the octet rule. And as you go down, sometimes you see variations from the octet rule, especially for things that are lower down. Sulfur, for example, sometimes phosphorus. And that's because what's happening is what's happening with the octet rule is the octet rule says that the atom is filling the s orbitals. Remember, there's 2 electrons in each s orbital that are over here. And then there are 3 p orbitals. So this is px, py, and pz, each 2 of these electrons. But these elements that are farther down can access their d orbitals. So they can have more electrons in their outer shell. But we're really going to focus on the ones that are up here that follow the octet rule: boron, carbon, nitrogen, oxygen, fluorine, and to a lesser extent phosphorus, sulfur, chlorine, and then bromine will pretty much always follow the octet rule as well. So that's where the octet rule comes from, and that's what's going on with these covalent compounds. So going back to my whiteboard for just a moment. So, and there's some symbology that we need to go over. So remember, I drew the electron dot structure for methane like this. Just to emphasize that these 2 electrons here, represented by these 2 dots, are forming a bond between carbon and hydrogen, right? Carbon and hydrogen are sharing those 2 electrons, so that as far as carbon is concerned, it's got 2 electrons and hydrogen wants 2 electrons. But this is called a bond. And these are bonding electrons. And what we can do is we can use a shorthand notation for that and write this also as, where the dash between the carbon and hydrogen represents a bond, and it represents 2 electrons, right? Oxygen, which I wrote like this, where you've got a pair of electrons here and a pair of electrons here, and then 2 pairs of bonding electrons in between oxygen. You can write this as oxygen and then 2 dashes, meaning that there is what's called a double bond, 2 pairs of electrons that are bonding this together, right? So for example, if we looked at formaldehyde, CH2O, right? Then the electronic structure of formaldehyde would be carbon, which has 4 electrons around it. And then hydrogen comes in, and another hydrogen comes in. And then we have an oxygen that's going to have 2 lone pairs of electrons. And then these 2. So that both of these electrons here are going to come over here and form the double bond. And the bond structure for formaldehyde would look like CH, and then a double bond to O, and then, right? And so we can count the electrons around carbon, 2, 4, 6, 8, because each one of those dashed lines represents a bond with 2 electrons, 2, 4, 6, 8. And around oxygen, there's 2 from the lone pair there, 2 from the pair there, 4, and then 6, 8. And then hydrogen has 2 each, because each bond has 2 electrons. So when you write out these dot structures, which are called Lewis structures for molecules, every atom has to have 8 electrons around it. It's following the octet, except for hydrogen, which has 2, right? So one of the examples in the book is the Lewis structure of ammonium trichloride. Nitrogen trichloride. So nitrogen trichloride, which would be NCl3. So we have N, and then we have 1, 2, 3, and each chlorine has got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 7. And so we could write this as N. So this is the pair on the nitrogen, and then you would fill in all of the electrons around the chlorine, each chlorine. So that's how you draw Lewis structures, and it's relatively straightforward. It can be a little bit fussy, but there's lots of things you can do with Lewis structures that if you have the Lewis structure, you can know some things about the about the structure and the shape of the molecule that you're dealing with. So in a covalent compound, in general, the compound will have no charge. So for example, nitrogen trichloride doesn't have a charge on it. And in general, there won't be a charge, but there are such things as molecular ions, and we talked about that a little bit, I think. And here we go, clear, right? And so one of the classical molecular ions is NH4 ammonium ion plus, right? And then another one is carbonate, CO3 2 minus, and then phosphate, PO4 2 minus, right? So what's going on with these? I'm sorry, 3 minus for that. Okay. So what's going on with these is that the internally this compound is covalently bonded. So if we looked at the structure for NH4, well, we looked at NH3 and it was NH H H, right? And there was a lone pair here, right? Well, if we bring in another hydrogen, right, and now we're just going to bring in a hydrogen there, then what's happened is if you look at this whole molecule, is that N, and then we have H, 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 right? So this hydrogen came in, and now we have 4 single bonds to this ammonium molecule, this ammonium atom. Each one has 2 electrons. So this nitrogen atom, each hydrogen atom has 1 electron because it gets 1 from that bond, 1 from that bond, 1 from that bond, and 1 from that bond, right? So each hydrogen has the usual number of electrons associated with it. But look at the nitrogen. It gets 1 electron from here, 1 electron from here, 1 electron from here, 1 electron from here. It has 4. So that means that this nitrogen is deficit in electrons. It should have 5, right? Over here, this nitrogen had 5. 1, 2, 3, 4, 5, because it gets 1 from each bond, right? And nitrogen with 5 electrons has a charge of 0. Charge of 0. Nitrogen with 4 electrons over here has a charge of +1. So this whole thing, NH4, has a charge of +1, and it becomes an ammonium ion. But each bond between nitrogen and hydrogen is a covalent bond. Okay, it's kind of confusing, but it makes sense. Now, if we look at, for example, carbonate, carbonate looks like carbon, right? And it has 4 electrons around it. And then we have 3 oxygens. And okay, so now we need to 1, 2, 1, 2, right, 3, 4, 5, 6, 1, 2, 6. And this has a double bond. Okay. Okay. So you see what's happened here is now carbon, the central carbon has got 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, right? So let's rewrite this as C, O, O, double bond to this O, and then we have 2 pairs of electrons here, right? And carbon has got one electron here, one electron here, one from there, and one from there. So carbon has 4, right? Each of these oxygens has 6 electrons in them, 3 lone pairs of electrons around it, okay? This oxygen here has 2, 4, and then one from here and one from here, so it has 6, so its charge is 0, okay? And now this oxygen has got 8 electrons, 2, 4, 2, 4, 6, 2 from that, 2, 4, 6, 8, right? The central carbon has got 8, this has got 8. So, but if you count the number of electrons here, it has 1, 2, 3, 4, 5, 6, 7. So this has got one more electron than neutral, so this has got a negative charge here. And the same for this oxygen, negative charge here, right? 1, 2, 3, 4, 5, 6, 7 electrons, right? So this is where you get the 2 minus charges here, that they come about because each oxygen bonded to this carbon has a negative charge on it. But all of the bonds internally to the carbonate ion are covalent. That bond is covalent, that bond is covalent, that bond is covalent, and that bond is covalent. However, there's a negative charge out here on one of these oxygens. Okay. Right? Kind of confusing. Hopefully you understand that when we draw the electronic structure of carbonate, we have this, and then we have this oxygen, and then oxygen, and then there would be 6 electrons here. Now, how do you figure out Lewis structures? Well, Lewis structures are relatively simple, and there's a couple of good videos that I've linked to about drawing Lewis structures. Hopefully they're in the module section. So let me share my screen and we'll make sure that they are where I think they are. Wait a minute. Web browser, there we go. Module 3 lessons, yeah, Lewis structures. So there's one from Khan Academy, there's one from iLecture Online, which is quite good, Organic Chemistry Tutor, a Ket's book video, and then Organic Chemistry Tutor on exceptions to the octet rule. And those are just a few examples for that, of how to do that. But we'll go through a couple of them here, and then hopefully we can figure out some Lewis structures. So let's look at sulfur dioxide. Okay. I think, yeah. All right. So let's look at sulfur dioxide, and we'll try and draw the Lewis structure, and we'll work through that as an example. Okay. I don't think that's a weird one where it has breaks the octet. Okay. All right. So SO2. Okay. The way that the first thing you do is you figure out that for SO2, for S, you're going to get 6 electrons. And for each oxygen, you get 6 electrons. But there's 2 of them, so that means 2 times oxygen is 2 times 6 is equal to 12. And so your total electronic structure is going to have 18 electrons, 6 plus 12, right? And so you would put down your sulfur, right? And here you would just assume that sulfur is the central atom in this point. And there's going to be at least one bond between each oxygen. Okay. And probably each oxygen is going to be double bonded to the sulfur, right? And each oxygen will have 2 pairs. Right? And so now we can count this up, and we have 2, 4, 6, 6, 8, 10, 12, 14, 16. So we have 16 electrons around here, which means we need one more lone pair on sulfur. And what you're finding here is that sulfur, because it's in the third row of the periodic table, can violate the octet rule, right? So SO2, I believe that's correct. 2, 4, 16, 18 electrons. Sulfur has 6, I believe. Yeah, sulfur has 6, just like oxygen. So there's a lone pair on top of sulfur, right? One lone pair. And I think if we look that up, you would find that that is indeed the electronic structure for sulfur dioxide. And now you could do another compound. Where did my, just dropped my pen. Now what's going on? Oh, there it is. Okay, good. So now you can look at carbon dioxide, CO2. Right? And so for carbon, you get 4 electrons. And for each oxygen, you get 12 electrons. So the total is 16 electrons. And carbon is going to sit here with its 4. And then you're going to get an oxygen out here and an oxygen out here. And so we're going to assume that there's going to be a bond between each oxygen, 2. And then probably we're going to need double bonds here. So now this has 2, 4, 6, 8, 10, 12, 14, 16. So this has enough electrons, right? And you would and you can stop that this is a structure, right? Now, if you didn't know that was, if you're really confused about this, the way you would start is you could try envisioning other structures. So let's take a look at that and how that looked. Suppose you thought that it might be oxygen, oxygen, carbon was the structure of CO2. Okay, and let's see if we can get that to work. Remember, we need something with 16 electrons, right? And each atom has to have 8 electrons around it. Right? So if we went to this, the only way to get 8 electrons, well, so if we said, okay, well, let's now assume that each of these has a single bond. So we would put, because this central oxygen has to have 8 electrons. If each is a single bond, it's 2, 4, and then 6, 8, right? And then this would have to have another 6 electrons, right? Because each atom has to have 6. And this would have to have 6 electrons around it. And then if we start counting, we get 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So this structure here has 20 electrons. Can't be right because we only get 16 electrons for the atoms. So this isn't right. So then we could say, okay, well, maybe we can save some electrons by making these things double bond. Okay. Now this has got 8 electrons around it, and this needs 4, and this needs 4. Right? So that this now has 2, 4, 6, 8, and then 2, 4, 6, 8. So this has 16 electrons, right? So you would think, okay, well, this structure might be okay. But now one of the rules about Lewis structures is the Lewis structure that's preferable is the one that minimizes effective charges on the atoms. And so let's look at what the charges are on these atoms, right? Oxygen should have 6 electrons. Carbon should have 4 electrons, right? So let's look at this carbon. It has 2, 4, and then 1, 2, 6, right? 1 from each of those double bonds. So this has 2 more. So the charge on this carbon is 2 negative. Okay? And what's the charge on this oxygen? It gets 1 electron from here, 1 electron from here, 1 electron from here, 1 electron from here. So 1, 2, 3, 4. So this is 2 positive, right? And this oxygen is neutral. It's 0 because it has 2, 4, 5, 6, right? So now all of a sudden, the structure that we've written, even though it's got the right number of total electrons, it's got a 2 negative charge here and a 2 positive charge here. So we've got this huge charge imbalance in the molecule, even though overall it's electrically neutral, right? So we would think, okay, well, if we can write something, a structure that doesn't have that charge imbalance on it, then we'd probably be better off. And so let's try and look at one where we put the carbon in the middle. So I put the carbon in the middle, and we draw single bond to each oxygen, right? And we could try putting single bonds, only single bonds, and we're going to come out with the same problem we had before, that we're going to get too many electrons, right? So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So this was the same problem we had before. So instead, let's put double bonds in. And now this carbon doesn't need any electrons because it has 1, 2, 3, 4, and it has 8 total. And if we put 2 pairs here, then we get 8 on this oxygen, 8 on this oxygen. Each oxygen has 6, so there are no charges on that molecule. So even though this structure is correct in terms of balancing electrons, this one is by far preferable. So we would assume that this is the structure that we look for. So you have to calculate the charges on atoms. And I know this is horribly confusing. And Lewis structures are a really useful tool in chemistry to think about molecular structures. And we'll see how we can use them to figure out how we can look at the actual shape of molecules using Lewis structures, even though this is a highly idealized sort of drawing here, right? So, so those are Lewis structures for covalent compounds. So now I want to talk about something else that covalent bonds do, and that is the fact that not all covalent bonds are equal. And what that means is, remember, if we go back to this silly cartoon I had here, where hopefully, yeah, right, we're sharing this, where the electrons are sort of shared between here. If the two atoms are the same, like here we've got 2 chlorine atoms, the two atoms will share those electrons equally. But if one of these atoms wants to has a greater affinity for the electron than the other, then the electron will spend more time around one atom than the other. And when that happens, there's a polarity of the bond, that one of the atoms becomes slightly positively charged and the other becomes slightly negatively charged. And we call that polarity, right? So we call that polarity. And you can tell what bonds will be polar and what bonds will not be polar by looking at something called electronegativity. Electronegativity. And really that tells you is the affinity a particular atom has for accumulating electrons. And you can look at electronegativity in terms of the periodic table. Go back to my periodic table. Where did my periodic table go? There it is. Right. I have to do the new shell. There we go. Okay. So electronegativity for atoms increases as you go up a column. So that means nitrogen is more electronegative than phosphorus, meaning nitrogen would rather take electrons than would take electrons more than phosphorus. And it also increases to the right along a row. So fluorine is the most electronegative element there is. Chlorine is a little bit less. Oxygen is less than fluorine. But chlorine is greater than oxygen. So it sort of increases kind of like this in a diagonal going upwards, except that helium, neon, argon, krypton are not very electronegative at all. So electronegativity goes up like this, and you could sort of figure out what bonds will be polar and what aren't by looking at the position of two elements on the periodic table. So for example, nitrogen is all the way over here to the right. Hydrogen is here. So when nitrogen bonds to hydrogen, it's going to be a very polar bond, and nitrogen is going to take most of the electrons away from hydrogen, and hydrogen will be slightly positively charged, and nitrogen will be slightly negatively charged. Oxygen bonding with hydrogen, same thing, right? Fluorine bonding with just about anything else is going to create a dipole or a charge on the fluorine, because fluorine is going to take electrons sort of away. Not completely, they're not completely gone. We're not ionizing things, but the electron spends more time, if you will, around the fluorine atom, so it becomes slightly negatively charged, right? And so polarity is a thing, and electronegativity is a thing. And I'll let you read about that more in the book. And I'm pretty sure there are some videos about that as well. Let's see here. Chemical energy, I got covalent bonds. Yeah, so there's a bunch of stuff in here. And then there'll be stuff about that down here when we talk about molecular geometry. Okay. So keep that in mind, and covalent bonds can have different lengths, as they talk about in the book. They can have polarity, and then we're going to talk just a little bit now about how you determine shape from molecular structure. And for that, I forgot to get this website, so we need to go to find PhET. So we'll go to PhET, and we'll find the online simulation chemistry and general chemistry, build a molecule, molecular polarity, come on, molecular shapes. Here we go. You run the thing. So we can use this to model molecules, but first we'll look at some real molecules, and we'll run this. And so we'll look at H2O. And what you can see here from H2O is if we rotate it around, right? Well, let me draw the Lewis structure for H2O first. Right, so let me go back to my whiteboard, right? Right. So if we're drawing H2O, it has an oxygen and then a hydrogen and a hydrogen, right? Well, hydrogen can only form one bond, so each hydrogen is bonded singly to the oxygen. And now oxygen needs to have 6 electrons around it, so it gets 1 electron from there, 1 electron from there, and then it'll get 2 more from here, right? So we get, why is my computer chirping at me? I don't know why it's yelling at me. Okay, so we get 2, 4, 5, 6. So, and the total number of electrons is 2, 4, 6, 8. And we get 2 electrons, 1 from each hydrogen and 6 from the oxygen, so 8 electrons. So this is the correct Lewis structure, okay? This doesn't tell us anything about the shape of the oxygen molecule, but we know the oxygen molecule has 2 lone pairs and then 2 single bonded hydrogen atoms. And now if we go back and look at the molecular structure, let's see, go back to new share. In our molecular simulator here, you can see here's our oxygen molecule. Let me rotate it down. So this is a hydrogen here. This is a hydrogen here. Here's a central oxygen. You can see that the oxygen is bonded here. And then if we spin this around, here are the 2 lone pairs. And what you can see is the overall molecular geometry is sort of like a tetrahedron, right? This goes up, these come down in sort of this bent triangular fashion down here. This is a characteristic shape called a tetrahedron, right? So what's happening is these electron pairs are both negative, right? And so they're kind of repelling each other. And so they repel each other and spread each other as far apart as they can. but they can't get too far apart because they start to feel these two hydrogen atoms, right? So they repel and then they sort of feel the electron clouds down here. And so they can't go all the way, right? And this is what's called valence shell electron repulsion theory. And by knowing the number of lone pairs on the atom and then the number of bonds in the other atoms bonded to it, you can sort of figure out what the geometry of the atom is. Okay, so we can look at another one. Let's look at sulfur dioxide, right? Which we remember we said it had two double bonds and then it had the lone pair. And so sulfur dioxide is this linear bent molecule, right? Where the two oxygen atoms come out at an angle, and then here's this lone pair that's forcing these oxygen atoms away from it, okay? So there's sulfur dioxide, right? And you can sort of drag them around. CO2, which we also did, no lone pairs, and it's linear. It's straight, right? Okay. What's another one? We did ammonia. Here's the lone pair on ammonia, and you can see it's tetrahedral, just like water, except here it's just got one lone pair. And then these three hydrogens are symmetrically arranged in a triangular pattern. If I can show you that, yeah, there. See, they all come out, but they're bent down. So this is a tetrahedron again. And so if you look at the model for this, you can start to put in things like a lone pair and another lone pair and another lone pair, and you could get these different molecular shapes with this. So this is kind of an interesting tool to fool around with. And if you're trying to figure out molecular shapes, this little tool from PhET Molecular Simulations is a useful thing to play around with. Right? So I'm going to stop there, and I think the next video I make, I'll work through some of the examples in the MyOpenMath section, and we'll go through with some of this stuff. All right, and I'm going to stop there, and I will talk to you later.